Okay, so the topic of our project is the Telesurgury robot, and we put together this mural of all sorts of things just to make our project extremely relevant. You can see that this is Shiloh. This is Dr. Colston, and next slide. We chose to work on a telesurgery robot because we think there's a lot of things that can be improved with surgery right now. One of those things is human error from the surgeon. Another major benefit of having a robot do surgery is that it doesn't require a surgeon to be in the same room as the patient. And this can open access to third world countries and people that might not have access to good medical care. And in time-sensitive situations, we could also get surgeons working on people that need care. In order to have a robot that can accurately reflect the intent of the operator, we thought we needed 0 steady state error, 0% overshoot, and a small rise and settle time.
In order to model the telesurgical robot, we chose to use the model and circuit diagram for an electric motor with the diagram shown above, which involves a circuit supplying voltage to an electric motor, which turns a mass, and then there's also a spring and a dampener involved. And we got values for all these components based off of references to modern instruments and the current Da Vinci machine that's being used as a telesurgical robot. So things for like resistance, impedance, the spring constant, things like that, we all just got from references. And we also had to model the loads impedance diagram circuit, which is on the bottom. And that helped us to decipher the torque versus position based off of the voltage that was applied. The resulting block diagram for the entire system is shown here, where it is a feedback loop in and of itself. And the KT and KE values were also just deciphered from references. The following block diagram is how we received the transfer function for the entire system, and it accurately relates the output position of a medical device versus the input voltage given by the surgeon. And by also adding an S to this transfer diagram, we could turn the output from being angular position to angular velocity. As a result, simplifying these two gets us the transfer functions below, where the first one on the left is the voltage versus positional output, and the one on the right is the transfer function for voltage versus angular position or angular velocity output.
Analyzing the system that we decided on, you'll see that our angular position goes off to infinity and it never levels out. This normally would be a problem, but since it is talking about position, it isn't, because as a constant voltage is being input into the system, the arm will always be rotating or moving in some way. So that would make sense in this case. Whereas our angular velocity is actually leveling off, and it has a settling time, which is approximately 1.7 seconds right now. And right now it has a little bit of overshoot, which wouldn't be ideal in our situation because it would lead to error in where it was cutting, where the telesurgery robot was cutting into the patient. However, it does settle off, which is acceptable because we don't want the robot to continuously be speeding up through the process. And so making sure that our system was stable, we did the pole locations, and as you can see, all of the pole locations are either at the origin or on the left-hand side of the plane. We need to be careful when we're adjusting our system, however, because if we increase the gain too much, then the poles will end up in the right-hand plane, which will then make our system unstable. We also did a Ralph Horowitz calculation, which shows that all of the coefficients are positive, which means that there are no poles, which is proved in our root locus that we provided here. and it also ends with 0. So our system is stable.
Still recording.
Yes.
She's still on the
It's
shot.
been recording since you started.
Sweet.
Oh my god, I'm so sorry. We decided to use PI controller because when using PI controller, there's no steady state error. Also gives us a chance to control the percent overshoot, which we decided to set to 0 because we don't want, the thing to just go and cut people where it's not supposed to cut. And other things like that. And it also reduces our rise and settling times that we're able to do the surgeries in a timely manner. And this is our block diagram for having the PI controller in with the transfer function and then so we use MATLAB's SISO tool and also the PID tuner to find our KP and KI values. So our KI ended up being 5.741 and our KP value ended up being 1.87. And this got us to a rise time of about 0.24 seconds and settling time of 0.36 seconds. And so then this also gave us a percent overshoot of 0, and our steady state error was also 0.
Yes.
All right, Maya, you got this one.
Brilliant.
All right.
Absolutely brilliant.
So with our PI controller implemented into our feedback system, with our PI controller implemented into our feedback system, we have a low rise time, a low settle time, 0% overshoot, and no steady state error. And when we set out with our design, those were important to our feedback system so that our robot would accurately reflect the intent of the surgeon.
Give me a chance.
That kind of works.
Oh.
Should I just